Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Kit Parker, who is a professor of Bioengineering and Applied Physics in the School of Engineering and Applied Sciences at Harvard University. Kit is also the director of the multidisciplinary SEAS Disease Biophysics Group. Kit researches cardiac cell biology and tissue engineering, traumatic brain injury, and biological applications of micro and nanotechnologies. Working in both biometric microsystems and programmable nanomaterials, he is involved in projects ranging from developing nanofabrics for applications in tissue regeneration to create organs on chips to address diseases such as asthma, muscular dystrophy, diabetes, brain injury, and others. Welcome, Kit.
Thank you for having me.
So, there are a lot of interesting things that you have been involved in over the years, especially in the biophysics group at Harvard. One of the areas there's a lot of interest in and a lot of work has been done is in the nanofiber area. And, from my perspective, material sciences, I would argue, has sort of underperformed compared to many other engineering domains. But, when I was going to engineering school in India, my professors used to tell me that material sciences is where the battle is going to be won because, innovation there could have very, very broad applications. And so nanofibers, you are designing, clothing, extreme temperatures, armors, things that could resist explosions and so on. Do you want to talk a bit about that area?
Yeah, sure. So why don't I start how I got interested in this? I was in Afghanistan in 2003 and I got called into a situation where a 5-year-old child had been burned. He'd been effectively dipped into boiling water up to about his chest, and it was horrific. And he died, but it was about as awful as you could possibly imagine. And I came back to Harvard to start my lab after my first tour in Afghanistan. And you can't see something like that. It impacted me and my guys in the events surrounding what happened with that kid getting burned and what happened immediately after were pretty horrific. And I have this incredible platform at Harvard. I was studying mechanotransduction in the heart, and the more I thought about extracellular matrix networks in the heart, I just couldn't help but think about the kid. As soon as I saw him, I knew he was going to die. It was too much surface area. I just knew he wasn't going to survive, and the burn was too bad. And so I started thinking about this protein called fibronectin, which we use with cardiac muscle cells, because there's something really interesting about this protein. It turns out when you do a surgery on a baby that's in the womb, when they're born, there's little or no scar. And it's because there's a lot of this protein called fibronectin in their skin. And over time, with age, the amount of fibronectin in your skin goes away. So it dawned on me that maybe you could come up with a wound dressing with this globular protein that you could have scarless wound healing. Thinking about that kid who got burned. So I had this, but it's a globular protein. You got to unfold it. So I had this idea that I could use a cotton candy machine and spew this globular protein out of a nozzle, and the shear forces would unfold the fibronectin and induce fibrillogenesis. Because no one's ever been able to use this as a building substrate, an engineering substrate. You know, some engineers build things out of concrete, steel, various, plastics. I build things out of cells and proteins, and cells obviously have a vote as to whether or not I'm going to have a good day or not as an engineer. Fibronectin is one of the ways to help cells vote the way you want them to have votes. So we had I had a fantastic postdoc in the lab at the time, Mohammed Badrasameh. We basically took a centrifuge motor off of a centrifuge and hooked it up to a cotton candy machine. We were able to make these fibronectin fibers, did some wound experiments. We're continuing those, and it opened up this whole idea of building nanofiber wound dressings for children. And obviously they're applicable to adults. But this whole avenue of developing nanofibers expanded out. We started thinking about my daughter was born with a murmur, right? And I'm looking at this, I'm thinking I need to build this kid a heart valve, because children, who have problems with heart valves, the problem is they have to have the heart valve replaced every few years because they outgrow what's been put into them.
Yeah.
So you got to crack the chest on the kid and put another one in. So I hired a postdoc, Kartik Balachandran, who's now professor at University of Arkansas, and we did our earliest work on a heart valve, and now we've got a heart valve in animal trials with our collaborators over in Zurich, Switzerland, Simon Horstrup. So, but then we start thinking about other things you can do with fibers. We start thinking about making, we're doing packaging for food. We started making tissue engineered meat. We've had a lot of soldiers that have had urogenital injuries from IED blasts. We started thinking about Kevlar nanofibers so we could make your underwear that offered you some type of ballistic and thermal protection. A graduate student showed up in my lab who was interested in cosmetics, and it turns out there's this huge environmental impact from cosmetic face masks that don't biodegrade. So we developed a technique for making biodegradable cosmetic face masks with some of the same technology we've been using to make wound dressing, soy, which releases the phytoestrogen. So we run the lab kind of like a gypsy camp. We develop some core competencies, and people have visions of what they want to do with them. And everyone comes in. So along the way, we've had people like Lululemon, Tory Burch's team, Nike, Reebok, Kraft Foods. I mean, it's just like this parade of cats coming through the laboratory to talk about what they're interested in. And we learn a little bit from every one of them. And several years ago, I got kind of frustrated with the creativity of the scientists and engineers, or at least the model for trained scientists and engineers. So we ripped out part of my lab and made studio space for artists. Yeah. So now we have artists in the lab, and they know a lot about material science, especially textiles. So between the people from fashion and beauty, Estee Lauder, the food companies, the fashion companies, medical device companies, Medtronic, Edwards, we learn a lot. And they just come and hang out for a day. And so there's lots of cool things you can do with this textile work. And if you show up and you got a problem, we'll sniff at it for a while and see if we can help trim the edges on it.
Yeah, such a broad area. So structurally, Kit, what is the attractiveness of nanofibers? So if you think about wound healing, what makes it attractive in wound healing?
So your skin, biological tissues are held together by protein networks called extracellular matrix. Yeah. And, imagine, like a loofah pad you scrub your elbows with in the bath or the shower. If you decellularize an organ, take all the cells out, you'll be left with a protein network that looks a little bit like a loofah pad. And that protein network are all nanofibers. It's all protein nanofibers. And so the nanofibers, cells are designed so that they can read they get various cues and instructions on how to behave and how to build themselves and how to build tissue from these nanofibers networks called extracellular matrix. So we just started mimicking that. And then we realized that you could take this bio-inspired design for extracellular matrix and you can apply it to everything from body armor to face cosmetic mask and clothing or whatever. So it's been just a lot of fun. It's this huge creative cycle that was bio-inspired, was inspired by a kid who didn't survive, and now we've done lots of different stuff. So
it's sort of like you're providing a scaffolding type environment so that you can get the cells to grow in a specific fashion. What is the action there?
So you know how when you build a house and you frame the house,
yeah,
you put a wooden frame up there, and then you're putting sheetrock and stuff like this. So that wooden frame in the house is kind of like the exocellular matrix, and so you can read it like cells read it like a map.
Yeah.
Hey, this is where to go, and this is what I need to be shaped like. Now, the other thing though is that embedded in this structural frame of the exocellular matrix network is chemistry that has other information. So the cells are reading information from this network that's guiding their behavior. At the same time, the cells can secrete their own exocellular matrix proteins and rebuild that network. So there's really a read-write relationship between the exocellular matrix proteins and the cells. And so that's important in development, you know, when you're growing, when you're forming. It's also can be a maladaptive when you have disease, like fibrotic heart disease or maladaptive scarring from a wound closure, things like that.
Yeah, and the extreme temperature applications of nanofiber. So there, again, you know, what makes nanofiber so attractive to extreme temperatures? The high temperature, you know, explosions, you know, those types of applications. What makes nanofiber more attractive there?
Well, I don't know if in our more particular work that's recently coming out on nanofibers, where we basically use the same material that goes into Kevlar. We made these para-amide fiber sheets that give this incredible thermal protection. Really, what it is we created an aerogel, and that allows a certain amount of thermal resistance as well as the ballistic resistance that we were looking for. But, you know, what we were able to do is get like a 20-fold heat insulation capability with these aerogels. And that was a pretty big deal for us. You know, if your firefighters at your local firehouse have their bunker jackets, their bunker gear has Kevlar in it that protects them from abrasion and from flame. And that's what we thought that we could do with a lighter material that you could put into an undergarment or maybe use for a drape in the operating room, because, you know, they have operating room fires.
Yeah.
So the whole idea of being able to make these lightweight materials that offered some flame retardancy, that's a big part of what we were, you know, trying to accomplish here.
There is, I would imagine, there's also some space science applications for it, right? Because of the strength weight ratio as well as the temperature resistance.
Yeah. So, I mean, obviously, you're thinking about cutting weight, you know, if you're doing anything in flight, and also just the ergonomics of having to wear heavy flame retardant stuff. So, you know, we've recently done some work where we took these gelatin figures and we put a blowtorch up to them, and we showed, you know, that these aerogels offered, you know, quite a bit of insulation. And you might have seen the videos. We published that paper, just came out in the journal Matter. And you know, this is obviously advantageous for if you're talking about children's pajamas. We used to worry quite a bit about house fires. If you're operating an operating room fire, or if you're on a vehicle, you know, you're a NASCAR driver, or any type of situation where you might be exposed to a thermal threat, having a lightweight material, these continuous fibers with strong mechanical properties that won't break down when you are exposed to that thermal threat, then you can hopefully survive it. That's what we're working on.
Yeah, I want to switch to another subject that you have done some work in. So that is lab-grown meat.
Yeah, sure.
And, you know, in life sciences, we know now what is bad for you and what's good for you. So if obviously the taste and texture of food is something that you get used to, and it's very difficult to switch out of. And so this sounds like something that has a lot of potential.
Yeah, so I tell you how I got interested in food. So many years ago, I got invited to be a judge on a Food Network show. And while we were filming, I would, in between breaks, I'd go and I'd talk to these chefs. And I was blown away by how much material science the chefs knew. They were making flexible chocolate. I'm like, how are you doing it? And they go, well, I'm putting alginate in there. And I'm thinking, alginate? Well, my colleague Dave Mooney, has been, the pioneer in using alginate for regenerative medicine. Right. And so I'm talking to these chefs, and these artists know material science quite well. So then later I got interested in the scientific aspects of barbecue. And, barbecue is when you're smoking meat, you're trying to break down really tough extracellular matrix networks in tissue so that you can chew it. And so I taught a class at Harvard. I went to barbecue judging school down at the Miami Culinary Institute. Me and my students spun off a company. We patented a smoker design. The company's called Dezora, and we sell the smoker with a company called Kamado Joe. And I spent a lot of time thinking about developing technologies to break down meat. But obviously, if you take a look at the environmental impact of meat production, farming, it's pretty extraordinary. And so we started thinking about, originally, we've been building tissues to go into bodies for a long time, heart valves and wound dressings. Why don't we just build a tissue that's going to go in through the oral cavity, something that you could eat? And at the time, I had some people in the group, Luke McQueen and Christophe Chantre and Grant Gonzalez, who we just started a company called Boston Meats to leverage the technology out of the laboratory. We started working on this. And every rule I learned about smoking barbecue, every rule I learned about making biological tissues for regenerative medicine was directly applicable to making meat. And the idea is, you're exactly right. Can you get taste and texture? And the other thing is, can you get the same nutritional content? So all the technologies we were using to make nanofibers are applicable to making the scaffolds that you want to build engineered meat off of. And when you're chewing into that filet mignon, the texture is an important part of the pleasure experience with the taste. And so that's why most of the engineered meats to date have been hamburger and sausage, because you don't have to have the texture problem. We think our technologies will solve that texture problem. So that's what we're focusing on.
Yeah. I've always felt that texture is a big part of taste, right?
Yeah,
it's sort of a simulated feeling in the mouth. So if you can replicate texture, I think you're, a good part there. This Impossible Burger revolution that's going on, I guess that is from plants, right? And that's again, there's a lot of texture related research going on there.
Yeah, and I should point out that our technology, we first started making scaffolds. Some of the stuff we were doing for wound dressings, we were using stuff like soy or alfalfa. The Shungkook Ong, who was a graduate student in my group, started using that because they have phytoestrogens in it. They're good for skin. Yeah. You can also use those scaffolds for food. So we are making completely vegetarian or plant-based protein meat products too. Mm-hmm. So we can use pea proteins and soy and alfalfa and other things. So our manufacturing technologies that we've invented are fairly robust in that they can handle animal or plant proteins. They can make scaffolds. So the idea of making an impossible filet mignon, completely vegetarian protein, but it gives you the same taste and texture of animal filet mignon. I don't know if that's going to be attainable, but we certainly have the technology to do that. More recently, my research group has started, so we think we've solved the texture problem. Now we've started working on the taste problem, and the taste in meat is always the fat, right? So we're just about to publish a result where we think we've cracked the code on how to grow fat and make fat fatter in a dish. And using these nanofiber 3-dimensional scaffolds. So if we can build the fat into our meat, then we can solve some of the flavor problems. So we're excited about this.
Yeah, in the long run, just thinking about, certain diseases like obesity that gets into type 2 diabetes, hypertension, which is probably half of our healthcare cost today, all point back to good food. So if we can manufacture good food and maybe in the long run even import some medication through the food.
No,
Yeah.
Gil, I think you're dead on. I think the early market of this,
Yeah.
I know they got stuff in Burger King. I know they got them in Dunkin' Donuts now that you can buy it at your Whole Foods. But probably the early market is medicinal foods.
Yeah.
Medicinal foods, I think, is the early market. You won't have to mass produce. You'll still be able to make your appropriate margins. You'll be able to deliver nutritional and medicinal content to the consumer. So I think you're dead on. The idea is your food as a medicine. Medicinal foods, I think, are the low-hanging fruit here.
Yeah, and it could have a huge impact on society, right? And the disease types, that commands a good part of the GDP are potentially easily, I shouldn't say easily, but potentially quite influenceable through food. And so I think there is a huge market there. I want to shift gears and go into another area that I'll start with a recent article here called Pancreas on a Chip. This is something that you're working on, right?
Yeah.
Today?
Yeah. So effectively what we were doing is, because of diabetes, there's various approaches. We were teamed up with Doug Melton, who has kind of been the big leader in developing cell-based therapies for diabetic patients. And so we were working with Doug on a NIDDK grant to develop a system, because before you can take a stem cell and grow it up into a pancreatic beta cell. But before you go and put that into a patient, you got to do a quality control check on this. And one of the biggest challenges we're having in the stem cell field right now is quality control manufacturing is just now entering the stem cell field. Unfortunately, we're really behind on that. And so in order to do that, you got to build some specialized tools. And the idea with this chip was to be able to take Doug Melton's cells, put them in there, and measure the insulin secretion when they go through various challenges, metabolic challenges. And so had a fantastic graduate student at the time, Aaron Gleiberman, just a master designer who designed this microfluidic chip. And as part of his thesis work. And, it's just, the system is robust. I mean, we're actually applying to the chip to other medical problems now too, besides diabetes. But now what we're doing is we're giving people like Doug Melton. Vertex Pharma has bought Doug Melton's company, and now they're moving towards cell-based therapies under the leadership of David Altshuler. He's the chief scientific officer over at Vertex, been on this diabetes fight for a long time. So now we've developed a tool where we can test these cells before you put it to a patient, make sure they're actually working. And that was the idea of doing a real-time ELISA assay. Right now, when they do the assay to check and see if these cells are secreting insulin, it's about 24 hours to get the results. We get it in real time. So this is a major advance forward in quality manufacturing for stem cells.
And so this is something that you could use to test medications?
Oh, yeah, sure. Yeah. I mean, like, and early on, that's what I think NIDDK was most interested in. And they wanted to develop an organ on a chip or a pancreas on a chip so they could look at the efficacy of various drugs that were going to do that. I took a very different lens on the problem. And the great thing about NIH is they give you a little bit of freedom to do that.
Yeah.
And I looked at it as a quality control tool. They want to look at real-time response to various pharmaceutical challenges so you can measure the efficacy. And there's not going to be a silver bullet to cure diabetes, artificial pancreas, cell therapy, or a drug. It's going to take an array of technologies. And so we're fortunate in that Aaron's chip design will support both the development of medicinal therapeutics and also cell-based therapies for diabetes.
Yeah. It's fascinating. You have another one in the same area. So taking the brain apart to put it all together again. So this is an organ chip system linked to a brain chip with two blood-brain barriers to understand the interactions between the brain and the blood vessels. You want to talk a bit about that?
Yeah, so that was a collaboration with my colleague Don Ingber over at the Wyss Institute. And we had funding from the Defense Advanced Research Projects Agency several years ago to do this. So we, I've been very interested in traumatic brain injury and other, neurological diseases in my group for some time. One of the biggest challenges with treating neurological diseases is getting the drug out of the cerebral vasculature and into the brain tissue. So there's a lot of work right now to understand the blood-brain barrier and try to understand how that might regulate drug delivery to the brain. We took a different approach to this. The idea was, are the endothelial cells in the cerebral vasculature providing some type of metabolic control or regulation over neural networks in the brain, besides just delivering oxygen? And so I had a fantastic postdoc at the time, Ben Mayos, who's now a professor at Tel Aviv University, who was working on this project with another postdoc from Don Ingber's lab, Anna Herlin, who's now a professor over in Europe. And what we found was that the endothelial cells that make up the walls of these blood vessels are acting like a metabolic throttle on the neurons inside the brain. Now, the funny thing is, when we built this system, we built a brain on a chip, and then we took two pieces of vasculature on different chips and coupled together so they were daisy chained. The way we tested this is we gave it methamphetamine. So, Gill, when your listeners are smoking meth, hopefully they're not, but, when you're smoking meth, what happens when you smoke meth is that you get a transient leak in your blood-brain barrier. It starts to leak a little bit. And what we showed was that when we gave our brain on a chip meth, the vasculature started to leak. So that's how we knew we had a functioning blood-brain barrier. We basically tested it with meth. And then we could dive into the really meaty metabolic challenges of that work. And then that's what we did. We poured that in Nature Biotechnology back in 2018. And now there's been a more recent paper showing connections between endothelial cells and other cells in the brain. So we've kind of opened up a whole new avenue of metabolic regulation of neural activity by just the endothelial cells.
So that's so interesting. So the leak that you talk about, is that one directional?
Oh, that's a good question. Well, that's going to depend probably on the interstitial pressure in there, whether you got fluid rushing from the brain into the bloodstream. I mean, it kind of depends on which way your pressure gradient is, right?
Yeah.
And I would imagine it's going to be primarily outward because of, your blood pressure is such that it keeps the internal, the internal pressures in those blood vessels are a little bit higher than what you see in the interstitial space in the brain. So it's primarily going to be outward. If you got pressure, if you got so much swelling in your brain that you're pushing fluid into your bloodstream from your brain tissue, you got other problems to deal with.
Yeah. No, I was, I don't know if it's even possible. I was just thinking that whether it has any applications in delivering, agents into the brain.
Yeah. I mean, that's one of the main things is can you do stuff to induce transient porosity of the cerebral vasculature so you could get large molecular weight therapeutic molecules into the brain tissue? And certainly that's what a lot of people are thinking about when they think about blood-brain barrier and organs on chips as a way to test, can we get some type of transient increase in the porosity of the vascular wall so we can get stuff into the brain.
Right. You also tried heart on a chip to speed up drug testing, right?
Yeah. So that the heart is my favorite organ in heart disease. And, we started our group many years ago. The primary goal was to understand how the heart builds itself. And we started from a cell, we went to tissues. And so we started this heart chip, not necessarily to test drugs, but we just wanted to understand how does the heart build itself? Because it turns out from about 2 days after you're born, the number of cardiac muscle cells you've got in your heart is pretty much what you have for the rest of your life, until they're treated by disease or heart attacks, things like that. So since these cells aren't dividing anymore, and different component parts from contracting all the time wear out. You talk about building an airplane while it's in flight. The cardiac muscle cell has to build itself effectively while it's in flight. It doesn't slow down, doesn't stop beating.
Yeah.
It has to replace these molecular motors, sarcomeres, and rebuild myofibrils and make extracellular matrix proteins and metabolize calcium and other things while it's beating. So a typical cardiac muscle cell synthesizes 5% of its proteins every day. That means every 20 days it rebuilds itself. So that's a big function. And so we had to build a system where we could study this in vitro while we measured tissue function. And so that's when we started the organs on chips work, which we've kind of, we were kind of the first group to come up with a heart on a chip. And we've been developing this technology for years now. We've moved to 3 dimensions where we're making small ventricles on chips. And it's been very rewarding. We've learned the fundamental rules by which a heart builds itself. And then we've been able to test various drugs and study different diseases with our collaborator, Bill Poo, who's a pediatric cardiologist over at Children's Hospital. And he's dealing with a lot of sick kids. So we use their stem cells to make models. And what we're going to go forward with, there's going to be an announcement very soon, is where we're going to model a clinical trial by taking these poor kids' sick cells, building a model of their heart in a dish, and testing drugs on them before we actually give the drug to the kids. So this is going to be a big step forward for the safety of sick kids, is being able to do clinical trials and get human data without getting patient data. And Bill Poo is really doing good work over there saving kids, and we're lucky to be partnered with the people at Children's Hospital.
Yeah, I mean, we are down a path, it seems to make it that, either biological or mechanical replacements of organs are going to be there, right? So it has some societal implications. What do you think? How do you think it'll pan out from a societal perspective?
That's a big question. My long-term goal is to build a heart for a sick kid. Pediatric diseases are my biggest interest. Pediatric cardiology is children born with malformed hearts, otherwise healthy. The idea is, can we build something that would give them a meaningful and long life? But so we don't really focus so much on the diseases that kill, the heart diseases that kill the elderly or older people, folks like us, Gill. Mostly on saving kids. I can have kind of a clear conscience of that. But you're right. What if everyone lives? What happens if all of a sudden the life expectancy around the world jumps 10 years? Do we have enough space? Do we have enough food? Here's the big one. Do we have enough water? What's going to happen? Are you going to have to attrit the population by war because the healthcare, as everyone's surviving, and will we adapt our ability to feed and house and get everyone clean water and education? If suddenly people start living a whole lot longer. And what's living? One of the biggest challenges we have here in America is that we suck at end of life. I mean, we absolutely suck at it. And like you go to a nursing home or hospice, I mean, there's people in there that are suffering, and we're keeping them alive at the expense of their dignity. They're in pain, they're miserable, and we need to have a discussion. A lot of this has come up during COVID. A lot of the people that are dying from COVID, these are, you get patients in their 70s and 80s, they've got all these other comorbidities. If they die of COVID, how many more life years were they expected to survive to begin with? This is a hard question, a really hard question. And it hurts when someone passes, right? Especially from a disease like COVID, where they're dying alone in an ICU on a vent and no one can tell them, I love you one last time. They can't tell their loved ones one last time, I love you. I mean, it's hard. And because it brings into and the reason, Gill, it's hard is because it's not just about the disease, it's about loneliness. And these people are dying alone in these ICUs. And, I have fought on the battlefields, Taliban, Al-Qaeda, and some other nasty cats. But the most dangerous enemy, the most cruel enemy I've ever seen is loneliness. And that's a part of the death of COVID. Your people dying alone. And we need to we're talking about vaccines and open up the economy and quarantines. What we need to do is talk about what it means at end of life in America, what it means to be alone, and are we actually being cruel when we extend someone's life several years and they have to live in a nursing home by themselves? They're in physical pain. They've lost their faculty. I mean, their senses. You know, I don't know what the right answer is, but we need to have this discussion.
Yeah.
And,
yeah. I fully agree. I mean, all the mental disease aspects as well, right? So we are very focused on the physical part of health. And, you know, this is part of the healthcare system has never really understood the idea that mental health and physical health are intimately connected.
Gill, and I tell you what we're doing right now as a nation is we're sacrificing our mental health for our physical health with this isolation.
Right.
I mean, there's a lot of people right now that are suffering a lot of effects of just being isolated for a long time. They're lonely. And that's part of the cruelty of this disease is once you get isolated, you're alone. And we really need to start, you know, in the military, we've really destigmatized in a lot of ways behavioral health care because we fought a 17-year war, right? Yeah. You know, you sprain an ankle, you go to the physical therapist, you know, your heart, your head, you're hurting, you go talk to a counselor, you know, and that's a social change that hopefully comes out of the military into the civilian population, destigmatizing behavioral health care. I hope it happens. I think the military is leading by example on this. But this is the eureka moment for the whole of the population, and that mental health is important. Behavioral health is important. And I don't think COVID is nearly as bad as the isolation these patients are feeling. The responsibility that these healthcare workers are feeling for patients who are dying alone. And that's really tough. So that's a hard thing. I mean, but we need to have some hard discussions about this.
I mean, you know this more than I do, Kit. You know, we have to prepare for a barrage of PTSD issues, just like, you know, people coming back from Afghanistan and other places, because we are going through a huge PTSD event right now.
Yeah, we are.
And you know,
and you're talking to a man who got help at the VA for post-combat stress after that. I saw that kid die. A lot of the guys on my team that were there that night had to work through that. And, you know, what I found when I was going through my counseling, I had a really good experience at the VA in Jamaica Plain and Bedford. Had a fantastic therapist who really was a kind of a warrior for me in terms of helping me work through some of these issues. And it was like, with my own buddies, no big deal. Go get some help. You're all set. I mean, you can't fight a 17-year war and not think your heart's not going to take a beating, you know?
Right.
And so I'm seeing the strain on civilian leaders, both in business and in healthcare, that are making decisions to survive companies by ordering people to come back to work or do things. And they're thinking about the moral responsibilities of their leadership.
Yeah.
You know, you wonder why a general can get post-combat stress? Because everyone thinks about the physical danger of combat, but no one thinks about the moral jeopardy of combat. And these leaders in the civilian population are ordering healthcare workers and first responders and people doing their job to go out there and do it and maybe be exposed to the virus. There's a moral responsibility in those leadership decisions that puts them at risk for some type of stress disorder. And it can be recovered, and you can actually have traumatic growth from it. And I'm hoping that we as a nation start to come to grips with the behavioral impact of COVID, and we look at this as an opportunity for traumatic growth.
Yeah, absolutely. I want to touch on something that you said before, Kit, and that is, you know, you asked, you know, as the population grows, do we have space, water, and so on? But what the numbers are showing, I don't know the exact numbers, is that population growth is actually slowing in most of the world. And, you know, so the replacement rate, as you know, is approximately 2.1. Most of the Western countries are below 1.7. The growth that we are seeing is happening in, you know, specific areas like India and other places. And so if you believe these numbers, what they're predicting or projecting is we will hit a population peak in the world by 2040 at just below 10 billion. And if you kind of follow that through, by 2100, the world population could lose 50%. So you could go from 10 billion to 5 billion in a matter of 50, 60 years. And so that, if that is in fact true, that has a lot of implications. I mean, we have been worried about resources, but if that is true, what that would mean is that, the value that we attribute to a human being is going to infinitely increase.
Yeah.
Right.
Yeah, sure. I mean, manpower is a resource.
Right.
Right? I mean, you own a business, you know that, right? It's a precious resource. So, yeah, I'm not familiar with that data, but it's pretty extraordinary. I mean, things are going to ebb and flow, right? Population will do that, availability of resources.
Yeah.
I don't know how they looked at changes in life expectancy as a function of that. When I was in Afghanistan, they talked about the infant mortality rate there is really high. What you've realized when you get there is if you ask an Afghan, a typical Afghan out in the southern Kandahar province, how many children do you have? And he says, I have 4. Well, later you found out he actually has 8, but he doesn't count the girls. So when you talk about your infant mortality rate, were they even counting the female children? They might not have been. So it's hard to get these kinds of numbers, but you get some indication as to what the infant mortality rate was. It was extremely high. I think at one point when I got there in 2002, it was 1 in 4, right?
Yeah.
Life expectancy of an Afghan male, I think, was usually in the mid 40s. So when you met an Afghan male who was in his 60s, that was a tough dude, right? Because he'd been through a lot. Beware the old man and the young man's game. But I don't know how they did calculations in increase in life expectancy, but you can take a look at crop yields with global warming. I mean, actually, we're producing tons of food right now, tons of food. And so how is that going to play out? If we got a lot of food, if you can solve the distribution problem, because we do have food insecurity in various countries where there's a lot of food, like in the U.S. How does that play out in terms of life expectancy? What's going to happen if we have some big wars? What's going to happen as the idea of warfare moves from blood and guts to science, technology, and cyber and money, right?
Absolutely.
I mean, anyone who doesn't think COVID is a war is crazy. This is the future of war. It's science, right?
That's right.
And the big question for people like me in the military is, are we really doing a good job defending the nation right now? Because we're under a full-blown attack,
right?
Just by a virus, right?
Right.
But you see other countries that are kind of exploiting this opportunity for cyber attacks to go after resources. I mean, this kind of things. This is the face of warfare in the future. Is you just build on natural disasters, or you exploit natural disasters to gain advantage. And so I don't know how they did those calculations, what they projected with, but there are some countries right now where you're taking a look at mismatches in the population demographics.
Yeah. Japan, as an example.
Yeah. Aging populations, and the question is, who's going to do the work? Right. I mean, especially aging populations, you got a cultural value of taking care of the elderly.
Yeah,
and that takes somebody off a factory floor, right?
Right.
So where's the manpower? Where are the people that are going to run this manufacturing and economic engine for these nations? I don't know the answer to these things, but I think it's a really interesting question.
Yeah, so many different things to think about. Like you say, COVID is an attack. It's almost like a bit of a tease in the sense that, there are certain parameters you can use to defend against it. We haven't done that very well in the US. But what may be coming behind it could be a lot more difficult to tackle. So this is a little bit of a training ground in some ways, right? But I don't know if we are really understanding it.
Yeah, I think the after-action reviews at every level after this are going to be really important, because if you're not looking at this as an indication of things to come, we've been building to this for a while, right?
Yeah.
We've had SARS, we've had all kinds of other stuff, diseases. And, we've, in the past, not necessarily done a good job responding to this. Public health people are there, they have interesting stuff, but then they get ignored, People still sitting on the couch eating fried foods all the time. Folks still smoking cigarettes, riding around without seatbelts and motorcycle helmets. I mean, it's just, people still behave like people.
Yeah.
But now we got a tough situation where everyone around you is a potential threat to you and your family unit, considering your family unit as a health unit, right?
Yeah.
And so now we're really kind of dependent upon each other. The scientific literacy of leadership is extremely important for countering these kinds of things, understanding the immunology and virology of these things and the public health issues. So I hope that this increases awareness of public health concerns.
Yeah.
I hope it starts a whole new discussion of public health concerns. I hope that we look at this as an opportunity not to isolate from each other, but to connect with each other with health in mind. And the question is, where's the leadership on these things going to be? It might actually come from consumer trends. A lot of the companies I've been talking to over the last few months, we've been talking about how will their product development change going forward. Well, there's two values that you're going to see coming out of here. First of all, sustainability is going to increase, maybe is going to be sustained, but also increase as a consumer value of the products they buy. But also healthcare, health, and signaling health. Hey, I'm healthy.
Right.
Talk to me. Interact with me. My family is healthy. Can I gauge the health of my family? I mean, you take a look at the company started by my students, Whoop, who were using wearable sensors, and they picked up the COVID symptoms in their patients, and they're probably not in our customers. 2 or 3 days before the onset of symptoms, they noticed increased in respiratory rates. Yeah. And just extraordinary success in predicting who amongst our customers was infected. I mean, the idea of wearable technologies that allow, like what Whoop does, is networked assessment or monitoring of your family. That's a pretty extraordinary thing. Right. And we can use that to help each other be healthy. And I'm hoping that technologies like that get broadly adopted.
Yeah, absolutely. Yeah. So I want to close, Kit, with this area. I want to get your insights on this. I think you're in the best position to assess this, having had experience in warfare as well as in an academic setting. And that is, as you see technologies develop, they're getting more complex. The policymakers, on average today, and this is true in the US, it's likely true most of the world, they don't really have the knowledge or information to make the right policy choices. So we are coming to a point that, we have a sort of a democracy-driven system and appointee-driven system, but it doesn't take into account competence or capabilities or understanding or knowledge, right? So do you see, as we go forward from a policy and system-wide perspective, there has to be some change in measuring competence levels in policymakers?
Well, the scientific literacy of leadership, not just in government, but in business, is being exposed right now.
Yeah.
Frankly, the hysteria, the press is not really helping because you're seeing crazy press reports about this, about that. And, the public is just at the end of this pendulum swinging around. Who do they believe?
Yeah.
The President's Press Task Force, CDC, World Health Organization, CNN, my neighbor, this woman I know at the PTO. I mean, where do you get your healthcare information? Mm-hmm. Are you educated enough to vet what is valid information? And in the early stages of a war, which it says it's very chaotic, it's very confusing. Yeah. A lot of misinformation out there. People want to believe simple answers. So you have to set the conditions to reduce this kind of chaos years in advance. Here's Parker's piece of advice. to prevent this panic, you focus on K through 12 education.
Yeah.
When you take a health class in high school, it's got to be more than the birds and the bees and wearing a seatbelt. You've got to understand why we do hygiene, infectious disease, and understand the impact of these things.
Right.
And so we really need to raise the bar in terms of what we are provide, the education we provide our children, and the scientific literacy of our leaders. Here's what you do.
Yeah.
You're like, okay, well, we got a Congress which is primarily dominated by people with law degrees. What do we do about that? and you ask Parker, and Parker says, well, that sucks, A. B, what you do is you go to the deans of the business schools and the law schools, and you say, okay, you guarantee that half your admits in every first-year class have to have a STEM degree. And you solve that problem, and then you produce lawyers who understand STEM. So, and you also alleviate some of the pressure on the lack of people in STEM careers in the U.S. Hey, you want to go to law school, get a degree in engineering, work for a couple of years as an engineer, then it's easier for you to get into law school. Do that. I mean, like that's an easy way to do this.
Yeah.
But I think also you got to think about the cultural changes in universities, Gill. I mean, like, take a look at that report that I think it came out of UCLA that shows something like 70-something% of college administrators have backgrounds in the humanities. But the trend of students in school right now is, I think, pushing 70% that are enrolled in STEM majors. So there's this huge cultural mismatch between the personnel infrastructure at a university versus the students versus the pool from industry and the professions, right? We need STEM people. But we're still going through a cultural evolution. I'm in an engineering school at Harvard, right? You want to talk about an epigenetic modification of a 300-something-year-old institution's core DNA. We're trying to turn this school into a school that values STEM and understands the culture around STEM. Explain that to my colleagues in the humanities. They see things very differently. Explain that to all the administrators we have. It's hard. So the key is education, building up the pipeline, but also looking at the infrastructure and thinking the quest for excellence in the sciences potentiates a very different culture for the quest for excellence in the humanities. And there's a huge friction point between that in most universities that has to be addressed. It has to be discussed, and it has to be discussed by university presidents. They're the only ones that are going to solve the problem.
Yeah, that's a great prescription. So both foundational education, but also as you go forward, sort of the portfolio of skills and knowledge that need to be there in almost every profession you can think of. So in some sense, my belief is that we have segmented education a bit too much, and it doesn't work like that anymore. Like you say, if you don't have a basic understanding of STEM, you cannot be a business person, and vice versa. Actually, I'll go in the other direction too. You could spend 24 hours in a lab, invent something, but it doesn't really have any practical applications. That may not be that useful either. So it goes both ways. But there is a need there, like you say, sort of assessing the portfolio that is optimum. Yeah,
I agree. I mean, like, the thing is you want to create a lot of talent, and you got to build the infrastructure to do that talent. But you have to have a culture that kind of supports the challenges of seeking excellence in engineering technology development. And I really wonder if the majority of universities are ready to support that. Yeah, MIT or Georgia Tech or Caltech or even Stanford, because engineering is king at Stanford, right? They get it. But you take a look at some of your Ivy League schools, some of your traditional liberal arts schools that realize we got to have engineering if we want to be a player in society.
Right.
But the question is has the leadership really set the conditions for the proper evolution of the culture on that campus to support that? And so, I mean, we're going through those kinds of growing pains now. And when I go over to Korea, I mean, like, I'm so impressed by the Korean universities and the value they put on education. I always say that Boston's a modern day Athens, but if you take a look at Seoul it's very close. I mean, they got some great universities over there, and they really value. Look what it's happened in Korea since the 50s. I mean, it's an extraordinary explosion of talent and industry over there, and they really put a value on this, and they made the cultural changes required to do that. And we're more heterogeneous in our population than Seoul, so our solutions won't look the same by any stretch of the imagination, but it can be done, and we can do it and maintain our values. I think as what we value as a nation in terms of our culture. So I'm hoping that happens. But the STEM development of leaders is being exposed right now, and if you don't realize that the world is going to be different after COVID, I mean, it's going to make the changes that happened after 9/11 look really tame. I mean, the world is going to be very, very different in the next 24 to 48 months. And the people that get ahead of these changes are the ones that are going to, benefit the most from them. But it's not business as usual is over.
Right. Yeah, let's hope for the best. This has been great, Kit. Thanks so much for spending time with me. And,
Yo, thanks. Next time you're in Boston, come on by the lab.
Absolutely, will do. Thanks so much.
There's always something cooking up there, sometimes literally.
Yeah, I forgot all my engineering, but I'll try.
All right, come on by. All right, Neil, take care.
Okay, talk to you soon. Bye.
Bye.